In this video, we're going to take a look at graphing and writing equations for piecewise functions. Piecewise functions are exactly what they sound like, functions that are broken into pieces. Typical form, you'll see f of x equals, and there'll be this little fancy bracket in the first equation with its domain, which is where we're allowed to graph it. A second equation with its domain, which is where we're allowed to graph it. These domains cannot overlap because it is a function. Now in this example, you see that there's going to be two equations, but a piecewise functions can have 3, 4, 5. It's endless. And we'll take a look at two examples where we go from the equation to a graph, one with two equations and another with three. And then we'll look at the example where we go from a graph to an equation. Now in all of these, we're going to keep them pretty basic, looking at mostly linear equations, so it's very helpful to know point-slope form. I put an asterisk there because I do look at point-slope a little differently. I look at it in what I call function form, where it's in y equals. And then what we'll have to do is just identify the slope, which will always be this position. We'll have to identify the x value, which is this position, and the y value, which is this position. Notice for the x value, there's a minus sign there, so that will always be the opposite of what we expect. Later on, this will also help you learn transformations if you haven't learned that already, where the m is the stretch or the shrink, and over here our x1 is shifting it right and left, and the y value is shifting it up and down. Let's go ahead and look at our first example. First thing I want you to notice when you look at these examples is what the domain is. So in our first piece here, we see that it's x is less than or equal to 1. So right away, I go ahead and I mark on the graph where I'm allowed to graph. So I see this is my 1, so I go ahead and I do a dotted line. And you can always go back and erase this later on. I'm going to leave mine on there so you can see it. And here I'm just going to write x equals 1, and we're going to be going to the left of that. And I'm just going to go ahead and extend it down just in case. You'll notice that it's point-slope form, perfect for us, so we can see that our slope here is 1/2. And our point, we have -3 as our x value, because it's the opposite, and here is our y value, which is 1. So our first point is -3, 1. So we're going to start here and -1, 2, 3, and up 1. There's our point. And then our slope is 1/2. So we're going to do rise over run. So up 1 over 2, up 1 over 2, and then we have to stop because we're on our boundary point. Now you'll notice that there's an equal to sign here. So our point is a closed circle. So it is closed. But we stop there, but we're allowed to continue left towards -infinity. So I'm going to go down 1, back 2. I'm just going to reverse the process. And we have it right there. And then we're just going to, play connect the dots. Well, we're connecting points. And to show it can go forever, we'll put our little arrowhead at the end of it. Now, our second domain for our second equation is x is greater than 2. Notice it's not equal to. So it's going to be an open circle, a non-inclusive point. So let's go ahead and find 2, which is going to be right here. So there will be a gap in this graph, and that's okay. That will happen. And that's at x equals 2, and we're allowed to graph on that side. So you'll notice that this is in slope-intercept form, something that you may be more familiar with. Noticing that the slope is 2. So let's go ahead and write that down. Slope is 2, also known as 2 over 1. And the y-intercept is -5, but that -5 is on the y-axis, which is on the wrong side. Now you could go ahead and graph it and erase points later on, but I'm going to take a look at another strategy. I'm going to look at making a table, and we have x, y, and I'm going to go ahead and plug in the first point I'm allowed to, which is 2, which is that non-inclusive point, so I'm just open circle. And what we're going to do is we're just going to go ahead and substitute 2 into 2x minus 5. So it's y equals 2x, and our x value is 2 minus 5. So we have 4 minus 5, which is -1. So we have the point 2, -1, over 2, down 1. So I'm going to have an open circle there with a slope of 2, up 2 over 1, up 2 over 1, and it continues. So we can go ahead and connect our points. And to show it continues forever, we leave an arrow there. So basically, when you're graphing these functions, you're always going to set up the domain on the graph first so you know where to graph. You're going to find a point from the equation you're looking at and use your slope to find another. You're going to draw a line that stays within the domain restrictions. And if you do get stuck, don't worry. You just make a table of values and you plot the points and connect them. Let's take a look at our second example. Looks a little more complicated because it is. I threw something new in there, which you'll see in a moment. But there are 3 pieces, and our first piece is x is less than or equal to 0. So let's start with that. So let's go ahead and just mark that on the graph. Here is x equals 0, which is the y-axis. And it looks like we're allowed to go to the left of it, so we're going to be on that side. And we're just graphing the equation y equals 4. And if you feel more comfortable, you can just come out here and just write y equals 4. And you should know that is a horizontal line. So we're going to go up 4, 1, 2, 3, 4. And this is our boundary point, and it is a closed circle, a closed point, because it could be equal to, so I'll mark it there. And it's just 4, and it goes left. All right, our second piece looks a little different because I threw absolute value bars in there. So we have -2 times the absolute value of x minus 1 plus 2. And if you don't know how to graph that, that's okay. We're going to take a quick look at it. But that's in between 0 and 4. On the 0 side, we have an open circle. On the 4 side, we have a closed circle. So we already have the 0, so let's go ahead and put the 4 in. 1, 2, 3, 4, and let's put our dotted line down there. All right, so it looks a little scary, but it does look like point slope. So we're going to treat it like a regular equation of a line. We're going to recognize that the slope is -2 on part of the graph. And then we have x minus 1, meaning we can use the point +1 and the y value of 2. So let's go ahead and plot that point, right 1 up 2, and put that point, falls within our domain. And then to the right of 1, the absolute value bars don't make a difference because something larger than 1, it will stay positive, and absolute value makes it positive, but it already is. So we can just go ahead and plot the line down 2 over 1, down 2 over 1, and down 2 over 1, and we have a closed point there. Now, on the left-hand side, the absolute value, we'd be taking the absolute value of something negative, so we're getting the opposite. Or you can just know absolute value graphs are mirror images on that vertex point right here. So there's our vertex point. So this is going to go down 2, but on the other side, and we have an open circle. And typically they're shaped like V's or upside down V's, you'll notice, and that is because of their symmetry. And absolute value graphs can be that easy, and that part's done. Graph number 3 looks a little different. I'm going to go ahead and write it down here. Y equals, I'm going to write it as a fraction, -1/2 x minus 4. And again, you'll notice it's slope-intercept form. Common mistake, some people just go down 4 and put a point. Don't do it. Go ahead and let's use our table of value trick. So we know we're allowed to start at 4, but it's an open circle. So I'm going to plug in the point 4, open circle, and let's do that here. Y equals -1/2 times 4 minus 4. So we get -2 minus 4, or -6. And then our slope is -1/2. So we're going to start at the point 4, -6 over 4 down. 1, 2, 3, 4, 5, 6. Open circle, and our slope is down 1 over 2, and then it does go off the graph, and that's okay, that happens. And there it is, done. Example 3. So example 3, you can see we're given the graph, and we have to come up with the equation. So what I like to do for this is I like to figure out how many pieces do I have to start. So we're going to look for wherever the graph changes direction, so we can see a change in the slope. So this is like first piece, and then there's another point here. We have a second piece, and then there's another point over here. So on this point, we have third piece, and on the right-hand side, we have a fourth piece. And what I like to do is I like to just go ahead and figure out what each of these equations are before I even look at the domain. So let's go ahead and take a look. So our first graph we see is just at 50 the whole time. It stays there. So we can say that's y equals 50. We're done. Our second piece, a little bit of trouble here. Some people struggle. This is where point slope is going to save us. Notice the point that we start with here is at 10, and it's at a y value of 50. So I'm going to go ahead and use point slope. Y equals, I'll figure out the slope in a minute, and it's just going to be x minus that 10 plus 50, because it starts at 10. X minus 10 after 10. And then our slope, notice we're counting by 5s on each scale, so I'm just going to go ahead and count by 5 and go up 5 over 20. So our slope is rise over run, up 5 over 20, which reduces to 1/4. So we can also see it's up 1 over 4 because it's the same scale. So we have 1/4, x minus 10 plus 50. Our third piece, I'm going to pick up at this point right here, which is at 30. with a y value of 55. Now I could use any point on these lines when I do this, but I like to use my connecting points. So we're going to have y equals whatever that slope is, x minus 30 plus the 55. Now our slope, remember it's rise over run, so I'm going to go down first. So we're going to go down 10, right 5. So we went down 10, right 5, which makes sense. It's negative. It's negative 2. So we have negative 2 right there. And our fourth piece, just a horizontal line. So we have y equals, and what is it? Just 5. Just y equals 5. Now let's put this all together. And we can mark our domain spots right here. This will be very helpful. So our first piece is between 0 and 10. Our second piece is from 10 to 30. Third piece is 30 to 55. And after that, it's 55 forever. So let's just put it all together. So we're going to have f of x equals, and we're just going to go ahead and make that fancy bracket that holds all our equations. And our first equation is 50. Our second equation is 1/4 x minus 10 plus 50. Negative 2 x minus 30 plus 55. And just 5. A little comma there. Now let's figure out our domain. First domain of 50 is in between 0 and 10. So let's go ahead and put that. So we start at 0, less than or equal to x, and then 10. Now I can include the 10 if I want, but since they're connecting pieces, I like to start that on the next one. This next piece picks up at that 10, and is less than or equal to x, and that goes up to 30. So less than 30. And again, I can choose what I want to be equal to and what I don't. It's the same point when they connect like that. So our third piece here is 30 is less than or equal to x, which goes up to 55, which is less than 55. And our last piece goes from 55 all the way to infinity, or we can just say when x is greater than or equal to 55. And it is that simple. Hope that helps.